Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Welcome friends. In this lecture, we are going to talk more in detail about the tubular connections. In the last set of lectures, we discussed about the design procedure for tubular members. We have used one international code of reference for getting the equations governing the design. We have also done one design example to check under biaxial bending and axial stress how a tubular member can be assessed for the loads acting on that. We have also seen the governing equations which help us to check the member design. We have learnt different aspects of design in terms of axial tension, axial compression, buckling, local, inelastic, hoop stresses, bending, hydrostatic pressure and ring stiffeners design, etc., which are all the governing equations given by one of the international codes what we referred in our lectures. Similarly, there are a couple of more which can also be used appropriately as the designer deems fit to use them in the design. Now, the members are fine. Now, the question comes, when the members are connected to each other, maybe on the same plane, maybe on different planes, which is a very quite possible configuration, then what will happen to the connections? So, now the question comes, the focus now on the epicenter of the failure now is vested with the joints. So, now welcome to lecture 36 friends, where we are going to discuss about the design of tubular connections. We will take up only the circular members in joints for discussion. Okay. So, when we say tubular connections, now it is very important to understand that strength of an in-plane tubular joint needs to be assessed for its fitness. Now, the geometric layout and the type of load or nature of load acting on the connection governs the design. Let us say the factors that governs the design, the geometric layout of the connection, then the nature of stresses caused by the loads. So, these govern the design. Friends, let us try to understand one more term where we say a characteristic strength of a joint. I am using a probabilistic term now. I think we discussed this in the last set of lectures. The characteristic strength which associated with the partial safety factors for material and loads. When we spoke about capacity and demand in the previous lectures, when we talk about the LRFD method, we talked about the probabilistic design rules. There we touched upon the characteristic terminology. The characteristic strength of a joint is essentially a lower bound estimate. Okay. In fact, the actual strength of the joint will be more than this. It is a lower bound estimate because we want to remain conservative in our calculations. Okay. To remain conservative, we always look for the characteristic strength of the joint, which is a lower bound of that. Therefore, what we do is, we will always use appropriate reduction factors, and these reduction factors are suggested by the design codes and they are based on experimental studies. So, friends, the equations govern the design are more or less empirical. Okay? They are not analytical equations. They are based upon certain factors which are derived based on experimental studies conducted on these joints on 1:1 scale. Okay? For example, if we talk about a cord connected to a brace, there can be many possible ways of connecting this. One can have a K joint, one can also look for a Y joint, one can also look for a X joint. We explain this in the coming slides, but it is very important for us to realize that the yield strength of the cord member is limited to or cannot be more than 0.8 times of the yield strength of the material. So, here we use a safety factor. Okay? Whereas, this is also limited to 500 megapascal. There is an upper limit on this number also. You may use steel of a different very high yield strength. We have already seen in materials part, yield strength can be as high as 1200 yield strength. Okay? So, but we do not allow that kind of yield strength in design. For cord members, we limit it to 500 megapascal. It is because of uncertainties, because of various practical fabrication issues, depending upon the observations made by experts during experiments conducted on their laboratory under test conditions, these recommendations are made by international courts. One of the important limitation why we do this, let me ask a question, okay. The one of the important limitation why we restrict this yield strength to 0.8 times of the material as well as not beyond 500 megapascal is that there is always a congestion of building at a connection. Though we say the minimum gap should be 50 millimeters and so on so forth, it may not be practically available there because of congestions, because a cord member can be connected to brace in all planes at the same point. So, we call this as build conjunction joint. There is a big congestion, and when the congestion happens, this may lead to strain concentration. It may also result in cracking, it may also result in laminar tearing. So, account for these in advance, courts restrict the allowable strength for design in connections in the cord member. Cord member is the main member, okay. Cord member not exceeding 80% of the yield strength of the material, but further limited to only 500 megapascal. Okay. Now, what care should be taken as a designer when you check the connections? Okay, let us ask this question. As a designer, in assessing the joint strength, the designer should ensure adequate through thickness toughness of the cord. This is a very important aspect. Sometimes because of material non-homogeneity, because of construction fabrication difficulties, the true thickness of the cord may not be there at the connection point. At the connection point, the cord thickness may get reduced. So, one should be ensuring as a designer that the cord thickness should have true thickness toughness. Okay? And furthermore, it is important to understand that the structural fit of a connection the structural the structural fitness of the connection should be assessed based on the nominal loads in the brace and the cord. Okay? You should not enhance the loads and then check the connection. It should be based on nominal loads. So, what do you mean by nominal loads? It is important to note that the strength of the joint of any joint, strength of any joint should at least have 50% of that of the member. We all know the joints are the weakest portion in a given system because members are checked for failure in different modes, whereas joints can fail at different instances. So, joints are the weakest segments, we all know that. So, one should ensure that the joint should at least possess 50% of strength of that member. Okay. The effective strength, to calculate this, compute this, is the buckling load capacity. Loaded either in tension, I should say loaded either in tension or in compression. This is for the member. Now, there are few basic properties which are useful in assessing the strength of the joint. Let us see what are those properties. Before we look into them, let us learn more about the philosophy of connections design. Cross sections of one or more tubes serving as braces can be connected to any cord. The connection is usually done by fusion welding. Fusion welding ensures complete penetration of weld. Okay, that is why we use fusion welding. So, connection between the brace and the cord is fully penetrated and we call this as fusion welding. Cord members at the connection may have special materials as well. At the connection a cord, for example, I have a cord member and I am going to connect a brace to this, I am going to connect another brace to this. So, at this segment of the cord member, I can have a special material coupling also, okay, and this material can be functionally graded material. We discussed about this in the previous lectures. Alloying steel can change its properties significantly. So, one can also alloy steel in such a manner that the strength, ductility and stiffness all can be enhanced by adding certain additive alloys to steel. So, we call them as functionally graded materials. So, one can also look for FGM enhanced connections in the cord members. Furthermore, friends, the load transfer process is simple. It is passed to the cord and which allows passing it through the skin. Cord is actually a hollow circular section. We know that is a main member. Okay. Cords receive braces from 3D axes. Therefore, it can be subjected to in plane and out of plane bending in addition to the axial stresses. I think in the last example, we discussed a member connection where the members are connected in causing in plane and out of plane bending. We did unitary check to prove and show whether the member is safe, not the connection. We are talking about the member. Similarly, a connection should also be checked for unity strength. We will discuss about that by taking an example in the coming lectures. Furthermore, friends, when you connect brace and do fusion welding to the cord, a major important problem comes in welding is ovalization and localized shell bending can happen, because the load on the brace is so high and it creates an unbalance between the brace on the same plane. It can cause localized shell bending to the cord at that connection point. Braces transfer stresses to the cord and they are all in form of line loads. Exact distribution of course depends on the relative flexibilities between the cord and the brace. Generally, cords are stronger than the brace. However, the load line distribution ensures or must ensure there is a perfect balance, so that there is no localized shell bending happens in the cord. Ovalization is a major problem which happens depending upon the D by T ratio. Okay. It also depends on D by T ratio of the cord and the brace, right. So, ovalization, whichever is weaker, it will get penetrated. So, one has to remember that this is a very important drawback when you do fusion welding in tubular connections. localized shell bending in the cord reaches its peak at these line loads and will follow a very steep local gradients. All of the above may induce punching shear, shell bending, in-membrane stresses, and combined effect of them may exceed the yield value of the connection. So, these local stresses are generally referred in the design as hot spot stresses. Okay? So, what are the consequences of a connection between cord and braces? I could say straight away the consequences are these connections are capable of inducing punching shear, shell bending, membrane stresses and their combined effect, which will exceed the yield strength of the material at that joint. We already said the cord strength should be at least 80% of the member strength in terms of yield value, right. So, it may sometimes exceed this, therefore, the cord will fail at local shell bending. Now, let us see how the connections are classified. Connections are classified by two ways. One, of course, based on the geometry, based on the shape. A single brace connected to a cord at an angle less than or equal to 90 can cause a Y joint, can cause a T joint. Okay? Can cause a Y joint or can cause a T joint. It is a shape, geometric shape. Two braces connected to the cord, either concentrically or with a gap, can fall or can cause a K joint. For example, I have a cord member, I have one brace here, another brace here, okay, with a gap between them. So, this can assign to be a K joint. Two braces connected to a cord opposite to each other can fall X joint. For example, I have a cord member, I have a brace connected to the cord, I have another brace connected to the cord here. It can be an X member, okay, it can be X joint. So, we have different configuration of joints as Y joint, T joint, K joint and X joint. These are all geometric configurations or classifications based on the geometry. Now, based on the loads carried by these braces upon the cords, we can also classify them as balanced and unbalanced connections. Let us see what is a balanced and unbalanced connection. Look at the K connection. K connection is this. Okay. The inward radial loads coming from one branch of the member are compensated by the outward loads of the member. For example, I have a cord member, I have a brace member, connecting load is axial compression, the other one is axial tension. So, these two can sometimes balance. Okay. So, that is called balanced K connection. By balancing these forces acting on the cord by the braces, one can minimize the ovalizing and therefore, the capacity can be enhanced and the resistance can be improved upon the local punching shear. So, when you have a connection where there is a balance happening between the load distributed by the braces onto the cord and geometrically it is a K connection, we call this connection as a balanced connection. Let us talk about an unbalanced connection. There is a possibility that the radial load coming from the single branch of the member is reacted by beam shear in the main member or the cord. This will cause ovalization and it will actually reduce the capacity of the connection. So, we call this as unbalanced connection. This can happen in Y and T connections. When we talk about X connections where members are connected to two different sides of the cord, maybe in the same plane, maybe on different planes, but there is an angle limitation to it. We will talk about that. For a cross connection or X connection, the load from one branch is reacted with the opposite branch. That is obvious, right? The resulting double dose of ovalization happens on the cord member. That is more serious because the cord member is now punctured at two surfaces. Look at this connection. Okay. So, there is a punching. Okay, let me draw it again. I have a chord member, I have a brace, okay. I have punching here, I have punching here, okay. Ovalization can take place at two places. So, the double dose can cause serious ovalization of the chord member, and of course, it causes more local stresses. Therefore, the load on the chord may induce now additional stresses depending upon whether this is a compressive force or a tensile force. Okay? So, as we said in the beginning, classification of joints come from three sources. One, of course, the geometric shape of the connection. Two, the axial forces being transferred by the secondary member to the primary member. Thirdly, is it in plane or out of plane? So, we have to be very careful about dealing with the connections design which is more sensitive or more prone to failure compared to the members. Now, let us look at what design methodology the courts adopt. When you have got multiplanar joints, for example, the braces are connected to the chord member from different. For example, let us say I have a chord member on my hand, it's a vertical member. I can connect one member on one side of the chord on the plane this way. I can take one more member connected to this side of the chord which is on a different plane. Okay? So, the chord being circular in cross section and shape being cylindrical, I can connect braces to any surface of the skin of this chord, right. So, I can have a multiplanar joint with braces coming into the chord from all directions. Okay. So, ideally speaking, the design methodology simplifies them into planar connections and then do it the design. So, there is an idealization done by saying if the angle of inclination of the brace member with respect to the plane of the chord member is less than certain amount, I can treat this as in plane connection or out of plane connection, vice versa. So, it is idealized as a planar connection depending upon the angle with which the brace makes with the plane of the chord. Therefore, as I told you in the beginning, based on experimental studies, parametric equations are developed. Different codes give you different set of equations. They have different kinds of parameters considered in the analysis of conducting these experiments, and they are empirical based upon certain standards derived by their experimental specialists. Therefore, all equations may not look similar, all parameters may not look same. Okay? However, you will find most of them are common to all international codes of design practices which are advocated in maritime engineering. The parametric equations are actually used for designing the planar joints, be it T, Y, K or X joint, does not matter, they are all governed by a certain set of equations given by the design codes of practice. So, analysis of these joints can be carried out using these parametric equations. So, what do we do in analysis then? Analysis will help us to find out the load capacity of the connection. Okay? If it is a biaxial or in plane out of plane bending causing the connection, then I will also do a unitary check. So, the connection strength is derived based upon the parametric equations. Okay? These equations generally account for interaction of braces from multiple directions. Okay? Therefore, analysis of planar joint is carried out in accordance with each category. For example, the parametric equations for T, Y, K and X connection are different. They are not same because the influence caused by these braces onto the chord, be it based on the geometry, the influence is different because one will cause double oval, one will cause oval on the same side, one will not cause oval but induce punching shear. So, the behavior of the brace upon the chord on different geometric shapes of the connection are different. Therefore, the consequences are also different. Hence, the parametric equations used for analyzing these planar joints are also different. Therefore, friends, the results of each brace are taken separately, and for designing the section or the joint, one must consider the maximum value. So, the design is always done for a worst scenario. Once you do this, you have to repeat this procedure for all the three planes where the braces are connected, and then one must consider the lowest one as the strength of the connection in the final design. That is the design methodology. Okay, I hope it is clear. Once we design it, let us see what is the failure criteria. How do we assess the failure? Capacity of the tubular connection based on different failure criteria. 1. It can reach the elastic limit of the material. Elastic limit is slightly above on a stress strain curve, is slightly above the yield point. Okay. We consider only the strength of yield till here, elastic limit can go here. Okay. We ensure that the steel still remains elastic till the point of stress considered in the design. Sometimes what happens, this yield value what you have accounted in the design may be exceeded. So, it can sometimes even reach the elastic limit of the material, and that can cause failure. Sometimes the material can also reach the yield strength. Already we said, probably you have noted that the strength of the chord members, which are the primary members, are considered to be approximately 80% of the yield strength of the parent material of the member, correct? So, we only take 80%, 20% we leave it as a reserve. Sometimes what happens, this reserve is overeaten, it can even reach the material strength, that is yield strength itself. So, that can also cause failure. Especially when you talk about tension joints, the first cracking happens at the connection, will start propagating, will start weakening the section, because tension will try to pull the joint. Pulling means the crack will get opened. Okay? So, that will also cause a failure. Lastly, the strength of the joint should definitely be more than the load coming on the joint, that is capacity versus demand. The maximum load of the joint sometimes may not be able to sustain the compressive force coming on the joint. Okay? Therefore, it can cause gross deformation in the connection, which we call as local shield buckling or ovalization. Okay? So, failure criteria and what are the different failure modes. The system can fail at connections. Let us take an example that the tubular connection is subjected to axial load and bending. The different failure modes are: 1. The cord can collapse. Okay, the cord can collapse. Secondly, cord can have a local failure because of ovalization or punching shear. There can be a progressive weld failure, because we are talking about fusion welding. There is a possibility that the weld will punch through the skin of the cord, can cause progressive weld failure. And lastly, there can be material problems, inhomogeneity, improper alloying of the material, improper fabrication, there can be material problems. Okay? These are different failure modes of a connection. Having said this, when we talk about failure modes, then we will take our understanding what we call as a general collapse. General collapse of a connection refers to gross flattening or distortion of the larger part of the cord. If the cord distorts or flattens up at a specific joint, we call that as general collapse. Sometimes when the cords and braces are intersecting, at intersection there can be a punching shear causing also a general bending of the cord wall. There can also be a general collapse. However, one can also look for local collapse of the cord. In the vicinity of the brace member, there can be a plastic failure on the cord surface along the load line of transfer. The punching shear can exceed the material strength at the cord connection, that can cause a local failure. So, there are different methods by which you can look at the failure modes and the failure perspective as well. Okay? Now, let us take up a simple understanding of a tubular joint and try to understand what are those parameters which are used in the empirical equations to analyze a connection of any geometry. Let us look at this figure, friends, on the screen. The empirical equation is based on certain parameters which we must learn. Let us see what are these parameters. If I have, okay, this is the cord member and these are all the braces, okay, As an observation, one can see the chord member diameter is larger than the brace diameter. Okay. So, the chord diameter is capital D and brace diameter is small d. Okay. And chord thickness is capital T and brace thickness is small t. So, small t refers to smaller in size, capital T refers to larger in size. Okay. So, chord members are thicker compared to the brace members. Okay. So, therefore, this is capital D, this is capital T, whereas this is small d and this is small t. I think that is understood. Capital D, small d, capital T, small t. Then let us talk about when two braces are connected on the same plane of the chord, then we need to maintain a gap. Otherwise, this will cause weld congestion, number 1. Number 2, look at the load lines. The load lines must intersect at the CG possibly of the chord to have effective distribution. So, you need to maintain a basic gap between them. You cannot have a connection like this, okay, because they will intersect here itself. You understand? So, there has got to be the load line transfer which will come and intersect more or less the CG of the chord member. So, to ensure this, you have to maintain a gap. The gap is identified as G and the minimum gap required is 50 millimeters, friends. Okay? Then of course, we try to find out an angle where the brace makes for the chord. So, measure the angle from the chord towards the base, okay, from the chord towards the brace. It is not measured this way. You may say the angle is always measured in any direction. How does it matter? Yes, it matters. From the chord towards the brace is theta. So, once these parameters are understood, then we have got certain dimensionless values which are now going to govern the empirical equations. Let us see what are they. One is called diameter ratio, okay, d by d, beta, and you will expect that beta will be always less than 1, right, because small d is greater than capital D. So, small d is always lesser than capital D. So, the range at which beta can be operated varies from 0.2 to 1.0. Okay. Secondly, the chord slenderness indicated as gamma given by d by 2t totally related to chord only. So, capital D is the diameter of the chord, capital T is the thickness of the chord. So, d by 2t is chord thickness, is expected to be in the permissible value between 10 to 50. Friends, these are all very important because the empirical equations developed by the code are all restricted to these data only. Okay. So, you cannot afford to have a connection which crosses the data. However, you will notice that this data range is widely covering all possible combinations of brace and chord connections which is applicable in reality. The third data, the parameter, is wall thickness ratio tau. Okay. Of course, this is ratio between the brace thickness to the wall thickness. Okay. Then comes the question of value of theta. The value of theta, the angle between the brace measured from the chord direction, is valid from 30 degrees to 90 degrees. The brace cannot be too horizontal to the chord, okay, cannot be less than 30 degrees. It cannot be close vertical to the chord. If it becomes vertical, it becomes a T joint, right? It becomes a T joint. So, the value varies from 30 to 90 degrees. You cannot have a flattened brace, you cannot have a brace like this. Okay. Can you tell me why? Very interesting question. Let us see whether you are able to answer this. If we have a chord, And if you have a brace very close, angle is very close, I have another brace also very close. Though I maintain the gap G, you know what will happen? The line of action of this load falls on the cord skin, which will create a punching shear to the cord. Okay? So, we should not allow that. So, we should allow a cord to have essentially some angle between them so that it falls into the CG of the cord. So, this angle permissible minimum is 30, of course, maximum is 90. Okay? Now, friends, strength of the joint is influenced by various parameters, is governed by various parameters. The first parameter what we think is a geometric factor, which is referred to as Q beta. The second parameter is the gap factor, which is referred to as Qg. You know, beta actually is the ratio between d by d. Okay, please note that. And this is G. So, Qg. The third one is it also depends on the nature of the load transmitted. Through the joint. Okay. Let us see some equations which will help us to do this. Let us say what is QB? Q beta. Q beta is given by 0.3 divided by beta minus 1 point, okay, beta minus, sorry, beta times of 1 minus 0.833 beta. This is true for beta greater than 0.6. For other values, Q beta is taken as unity. Okay? That is the first factor, which is called geometric factor. The second factor is called the gap factor, which is Qg, which is given as 1 plus 0.2 times of 1 minus 2.8 G by D the whole cube. This is true for G by D greater than or equal to 0.05. Okay? Otherwise, is greater than 1.0. Qg is also equal to 0.13 plus 0.65 phi gamma to the power 0.5 for G by D lesser than minus 0.05. Now, the question here is the phi value which we use here is equal to T times of FYB by TFY, whereas FYB is the yield strength of the brace. One can use different materials for yield. Approximately this is 0.8 times of the tensile strength. Okay. Now we have seen the G by D value varying from 0.05, let me do it very clear here, there is a dot missing here, 0.05, okay, 0.0, let me rub it and write, greater than or equal to 0.05, okay. So we have now seen a range of G by D from here to here, right. For other values, of G by D lying between minus 0.05 and 0.05. One can use linear interpolation to compute QG, the gap factor. Okay. Now let us say what is the strength factor for QU. One may notice in all these equations there are many parameters which are playing a role, therefore they are all empirical in nature. So one has to be very careful about the limits between which they are valid and about the ranges within which they are valid. So they are very important. Now let us talk about the strength factor for K joint. The strength factor for K joint is given by QU. Okay. Now QU under axial tension and compression is given by the following relation. QU is equal to 16 plus 1.2 gamma beta raised to the power 1.2 QG, QG already we computed, but cannot be more than 40 times of beta 1.2 QG. Friends, these equations are taken as a reference from the Design International codes. So, you can refer to these codes which are given in the list of references of this course and try to verify these equations for their correctness. Though I am trying to do my best to write them correctly during the lecture, but because of oversight, you please verify them with the original code of reference and correct them. If you find anything different, please let us know. Okay. The QU for the K joint is computed using this relationship. Okay. If you have something in in-plane and out-of-plane bending, then we can say QU is given by the following equation. Let us say this is in plane bending is given by 0.5 plus 0.7 gamma raise beta 1.2 Qu of the K joint for out of plane bending is given by 2.5 plus 4.5 plus 0.2 gamma of beta 2.6. This for the K joint. Okay. Let us now do for the T and Y joints. Under axial tension, Qu is given as 30 times beta. Under axial compression, Qu is given as 2.8 plus 20 plus 0.8 gamma of beta 1.6, but it cannot exceed 2.8 plus 36 beta 1. Let me write it here. But cannot exceed 2.8 plus 36 beta power 1.6. That is the limit. Okay. This is for the axial tension and compression for both T and Y joints. When they are subjected to in plane and out of plane bending, the T and Y joints, okay, their strength is same as K joint. Whatever equations we saw for the K joint, like for example, these are all equations seen for axial tension compression for K joint. Other than that, for bending in plane and out of plane bending, these equations are used for K joint, same or valid for T and Y joints also. Okay. Now, let us complete one more part and close the lecture. So, for X joints, because we have got different geometric configurations, we would like to complete them in one go. So, under axial tension, the strength factor Qu is given as 23 times beta for beta less than or equal to 0.9. For other values of beta, Qu is given as 17 gamma minus 220. This is for axial tension. Under axial compression, X joint, Qu is given by 2.8 plus 12 plus 0.1 gamma beta multiplied by Q beta. Okay, already we know Q beta. For in plane bending and out of plane bending, the strength of X joint is same as K joint. So, no difference in behavior. Okay. Let us also have one more issue related to the chord factor before we look into the interaction diagram and do a design example. Okay. So, friends, we will close this lecture here for a minute. So, let us write down the summary. In this lecture number 36, we learned how connections are important, what is a chord and what is a brace, which is the main member, which is secondary member, what are the geometric parameters which govern the design, how the joints are classified based on the geometry, based on the unbalanced and balanced forces acting on that. Then we learned that the strength of the joints are actually derived based on experimental studies. So, different codes consider parameters governing them and they give governing equations. So, we started finding out the strength factor for K joint, Y joint, T joint and X joint for axial tension, axial compression, in plane bending and out of plane bending. Okay? We learnt it. So, I would again request you to verify these equations for their correctness from the original code of reference, which is cited in the reference of this particular course, which is API RP 2A. Please verify to the latest revision of this code and check the correctness of these equations and also help us if there are any updates in these corrections which is not mentioned in the lecture. Hope you have followed this. We will again discuss further more on the connections. Thank you very much. Namaste.